Thank you, and thank you for everyone for attending the session. My name is Eric. I'm a software engineer from Cryptsoft. We are a company based in Brisbane, Australia, and we develop standards-based SDKs around KMIP and PKCS11. So key management and crypto integration is what we specialize ourselves in. And today, I'm going to remove some of the mystery around quantum key distribution, QKD. Some people think QKD is not even real, or there's no demand for it. And I'm going to explain how you can practically integrate QKD system with the existing system that you already rely on, like OpenSSL and Bouncy Castle. And finally, I'm going to outline some of the limitations around QKD, try to explain why QKD is not successful as it should be. Okay, so first, why QKD? Why we should even consider about deploying a quantum safe solution? Well, first, the threat from quantum is real. You have companies like Quantum aiming to build utility-scale, fault-tolerant quantum computer by the end of 2027, right in my city, Brisbane, Australia. And about $1 billion from the government has invested into that project. And when the world have access to a useful quantum computer, traditional encryption algorithms such as RSA and elliptic curve will become vulnerable. And even before that, there's the harvest now, decrypt later attack, which means attackers can just collect the encrypted traffic today and try to decrypt it when the tech become available. Quantum key distribution as a technology become available about 15 years ago, offering a promising solution against quantum attack. And lots of attentions and effort has been invested into the research and development of QKD, and now you see a collection of vendors offering commercial QKD solutions. Not just the big vendors like Cisco and Nokia, but you also see a collection of small vendors and startups even offering commercial QKD solutions. So we see about 30 startups in Europe alone offering QKD solutions. So in essence, QKD is real, it's been used in real life actually. And companies and organizations that are interested in deploying QKD solutions need realistic integration strategies such that QKD can work with the existing system. Okay, so the quantum threat costume, you can wear this next time to this conference. Guaranteed to get attention and terrified for anyone who does security for a living. And for now, at least, it is completely imaginary. But unlike werewolf, one day this might be real, and you don't want the person without the silver bullet. In our cases, PQC and QKD. Okay, so what is QKD? What is quantum key distribution? What is the science behind QKD? Well, in essence, quantum key distribution is a method that utilizes the fundamentals of quantum physics to generate and distribute a shared secret key between two parties. A good way to, it utilizes the fundamentals of quantum physics such that any eavesdroppers trying to compromise the event, trying to compromise the communication channel will be detected by both parties of the communication parties instantly. A good way to explain this physical phenomenon is by using Young's double slit experiment, which in the experiment setup, you will shine a light beam through two narrow slits, and you will result in an interference pattern. So photons will behave like waves, and you will see a spectrum of dark and bright strips on the wall. But the moment you set up a detector on the slit to check which photon passes through the slit, then the result changes immediately. You will have only two strips on the wall, and photons will behave like particles instead of waves. So in essence, measuring a quantum system will disturb the result. And for the QKD protocols, BB84 protocols in particular, it utilizes the same quantum principle. So for BB84 protocol, you will encode photons into two possible bases, one vertical and one horizontal, diagonal. And a eavesdropper trying to compromise an event by measuring those photons, but they don't know the correct basis, will introduce this error, which the error can be picked up by Alice and Bob, and they know that their link has been eavesdropped, has been compromised. So this is the known as the tamper-evident link property for the QKD, and that's the very reason why QKD is useful against quantum attack. Okay, so this is real-life QKD machines are commercially available for purchase. This one in particular is developed by ID Quantic, a company based in Switzerland. For the typical QKD system, a ground-based fiber optic QKD system, you will need 2 of these machines, one for Bob, one for Alice, and you will need a dedicated point-to-point dark fiber to connect those 2 machines. This setup creates 2 problems. One is that this setup is relatively difficult to scale because, well, it needs dedicated hardware, and hardware is expensive. And it's, there's a distance limitation for the QKD system at the moment. So about 100 kilometers, actually, before the system become unable to manage, and the losses of quantum signals, also known as photons, are too large to become useful. Once the QKD established, though, enables both sides to receive an endless stream of ciphers. So this essentially functions like a one-time pass situation, creates a, in theory, unbreakable encryption. So to summarize, QKD solution is real, but it's expensive, it is infrastructure heavy, and there's a distance limitation to the solution. And you can also deploy QKD solutions in space. So this is a QKD space satellite developed by Spectral, a company in Singapore. This is also a commercial solution for people to purchase. And, but the cost here, however, is at a complete different scale. So the total project include the satellite, the rocket launch, and the ground station to receive those quantum signals. That costs a lot of money. For one project that's commissioned by a European Space Agency, the total project cost is about 130 million euros. So very expensive. But the benefit here, compared to the fiber optic approach, is the distance, because quantum signals, also lasers, can reach a much greater distance over space, and up to 1,000 kilometers, 1,200 kilometers for experiments done in China. And there are other QKD methods in demonstrated capabilities in research. So the most, we see that the most commercial solution is the ground-based QKD solutions, fiber optic approach, but you also have underwater QKD and the drone-based QKD. So this is a demonstration, this is just a demonstration of the potential for QKD applications is there. There are things that can be benefited than in the QKD space. Okay, so we have previously discussed it on the QKD protocol, the BB84 protocols. It is part of the DV QKD, the discrete variable QKD technologies, and it comes with limitations. But we also have different techniques and technologies available. For example, we have twin-field QKD system that can potentially address the distance limitation problem. And we also have continuous variable QKD, which addresses the hardware problem by utilizing the existing infrastructure, so removing the infrastructure overhead completely. So this is the QKD and user market landscape. At the moment, we see that QKD users are primarily dominated in the government and public sector. So from university research project to government building a QKD network for testing. And it's also heavily implemented in the military and intelligence sector. But the usage for QKD in the private sector and traditional network security sector is relatively limited. But but the potential for having QKD to be benefited in that sort of sector is there. The potential is huge. Okay, now This is an example of a point-to-point QKD system integrating it to a traditional network security solutions. So in this solution diagram over here, we have all the hardware and software provided by a single vendor. You have QKD channel at the top established by either virtual or physical QKD. I will explain the virtual QKD later. And symmetric key are being shared and used to configure Ethernet encryptor. Protocols are being developed to standardize the delivery of quantum keys. This protocol in particular is the ETSI GS QKD014 protocol, developed by European Telecommunication Standard Institute, so ETSI. This protocol ensures that if a third-party vendors want to integrate with a QKD solutions, they can just use this protocol to be in theory utilized as QKD keys. So for this protocol, QKD machines will preview the QKD buffers with identical symmetric keys on both sides, and each keys get to associated with a UUID. During a key transfer, when an encryption key is needed, then you only need to send the UUID over the public network. You don't need to send the key materials because key materials itself is configured over the quantum channel. Yeah. Okay. Now, with this protocol, with this QKD014 protocols, now third-party vendors like link encryptors from Engage Black now can integrate with QKD's point-to-point QKD solutions. So you essentially you achieved here is a encrypted IPsec, encrypted VPN, but with the added benefit of IPsec pre-share key being configured over the quantum channel. So you essentially achieved is a quantum-safe VPN. And I'm going to explain what virtual QKD is essentially a software-based approach for the QKD. It utilizes the TLS, traditional TLS with PQC, TLS 1.3 with PQC, post-quantum cryptography, and with the PQC, and with the QKD protocols. It can be implemented using OpenSSL 3.5 and Bouncy Castle 1.81. It offers equivalent protection against quantum, but it doesn't have the tamper evidence link properties. So if you have if your company is trying to build a QKD system, you have all the hardware and software architect around QKD, but you're waiting for the machine to arrive and you're waiting for the fiber optic to be plugged in, you can use virtual QKD to prototype and prove and onboarding, migrating your employees to the QKD network. And there are existing QKD network available, and you have openqkd.eu in Europe, and you have very creatively named qkd.com. Okay, a side-by-side comparison. Obviously, virtual QKD is relatively cheaper because there's no infrastructure overhead, and it both offers the quantum safe. Both offers quantum safe scenarios, but for both virtual and physical QKD, there's lack of open standard. So there's minimal interoperability across different systems. Okay, so now we are moving for the QKD network. We have previously discussed the point-to-point QKD. Now we are moving on to the QKD network. So it's a three-layer architecture. At the bottom, you have the quantum layer. So it's essentially a collection of point-to-point QKD connections. And at the top, you will have the application layer, which is the the software and hardware that utilizes quantum keys. And at the center, you'll have the key management layer, the KMS layer, which serves as a network interface between the QKD machines and the devices that consume keys. And it does the important job of key relays between different QKD connections. So you're probably familiar with KMS, but quantum KMS is slightly different. So for a classic key management server, it's more of a centralized view for key management. So you will have all your keys stored in one place. But for quantum KMS, it's more of a network framework for routing symmetric keys to the application layer. For the classic KMS, you will have open standard available for interoperability. You have KMIP, you have PKCS11, but for quantum KMS, well, there are minimal interoperability. Different vendors provide their own vendor proprietary protocols. You do have the ETSI 014 protocols though, but it is only a key delivery protocol. It is not a key management protocol, which is only one function of many functions of a KMS can do. Like, for example, you want to what if you want to add attribute to a certain keys? What if you want to locate a collection of keys with similar attribute? That sort of things. There's no open standard. Okay, so this is a single vendor approach. Sorry. This is a single vendor approach for the QKD network. As you can see, from the application layer to QKD network layer to the KMS layer, all provided from one vendor. So QKD as a technology become available about 15 years from now. And the usage of QKD is relatively minimal, and it's so minimal that people in this conference don't talk about it. Why is that? Well, several reasons can be explained. One is that the technology is not being fully matured yet. There's so many limitations around QKD, and the solution is so expensive. There's high operation cost for QKD. But if you ask me, in my personal point of view, those are not real problem for QKD. As all the technologies moving forward and develop and more demand to it, the cost for QKD will be dropped. And there are technologies and protocol being demonstrated capabilities inside lab conditions that can address the QKD's limitations, such as you have twin field QKD that can address the distance limitation. So you have to be optimistic on the technologies. But I think the real problem that's for the QKD solutions out there, and it's relatively easy to solve, is the lack of standardization and compatibility. So there are minimal open standard for QKD. Okay, so one solution to address this problem is by adopting open standard. And a very common standard over there is KMIP, Key Management Interoperability Protocol. So KMIP is a client-server protocol that ensures different vendors' security system can work together. So prior to KMIP, different vendors, different security vendors would have their own key management protocols. If you are enterprises that utilizes services from seven different security vendors, then you need to implement 7 different proprietary protocols to your applications. And long came so it's KMIP, you have this open standard. And the spec is up there, is available for everyone, and you have test case available for everyone to test. It utilizes the open standard technologies to ensure that everyone can be worked together. Okay, so KMIP become available about 2010, so that is about QKD become available. Only 4 companies pushed that project and published by OSIS, the Organization of Standards, the Organization of the Advancement of Security Information System. And now, fast forward to today, over 100+ companies are offering security solutions with KMIP with KMIP integration into it. So why we have a bubblefish over here? So because KMIP essentially functions like a bubblefish. It allows different companies' solution system work together without having to test. So this is the ideal architecture for QKD network. The only difference here is having open standard KMS sitting in the KMS layer. So not only you have the ETSI 0 and 4 protocols machines benefited from virtual QKD or physical QKD network, now every existing KMIP applications that you use today can be benefited from a QKD network. So if you are an application programmer, like which approach will you choose? Will you choose the single vendor approach, which means you need to integrate every security vendor's QKD solutions, or you want to implement a single open standard, and potentially speaking to almost the majority of the QKD solutions over there. We have demonstrated this multi-vendor interoperability QKD network approach inside Cryptsoft environment. So we have established a virtual QKD using the qkd.com, handling the key share, and we connected using our KMIP KMS. So not only we have configured a secure IPsec VPN using the virtual QKD, but also we have existing system like NetApp, database from NetApp, or VM from VMware, all protected by quantum key distribution. So I'm just quickly going to introduce what KMIP is. KMIP is a very simple protocol, TTLV. This is a hex for the actual message. It doesn't make any sense to you, but once we highlight the element, the tag, type, length, and value, now it starts to make more sense. And by referring to our spec, which is available on our on the Oasis website, now the messages are making more sense. So this message in particular, it is about requesting a creation of a symmetric keys. And you can implement a very simple KMIP client on your application side using OpenSSL's sclient command. So you only need to construct a KMIP messages using our spec and encoded using binary, send it over, grab the certificate, and get the response and decode it using our spec, which is also quite straightforward. Using Bouncy Castle, it is slightly more complicated, but the idea is the same, right? Because Bouncy Castle doesn't provide the command line interface, but you will also send the encoded messages, send it back, and then decode it. OK, so QKD as a solution become available about 2007 and 2008, we see our first real-life demonstration of QKD inside a fiber optic network. And in 2017, 2018, we see that QKD network start to emerge from China to US East Coast to Europe. Now the QKD landscape is slightly different. We are no longer seeking to validate, seeking to prove that QKD system works, because we know it already does. Now we are looking for standardization and compatibility with the existing system such that QKD can be benefited by our existing network. And in the future, we will combine QKD with PQC and connecting those QKD network together, forming a global quantum secure key distribution network. So we know that classical crypto is compromised against quantum attack, but we have TLS 1.3 with PQC and QKD both as a solution offering protection against quantum computers. But the statistics tells you a different story. Last year, about 70% of total network traffic, that's the statistics from Cloudflare, are encrypted with PQC. 0% usage for QKD. This year, about 40% using PQC, and still 0% for QKD. And we firmly believe that this 0% will start to change if the QKD vendors out there start to embrace open standard. Thank you. That's my, I'm open to any questions.
Thank you very much for the talk. I wanted to ask what is the probability that it will actually stay at 0? Because post-quantum crypto can be run over the standard channels, right? You don't need to have a special ones. So it can actually stay at 0. What do you think?
Yes, I think you are right. The possibility for having a QKD solution as 0 is always exist. But we see that the market has become more and more interested in the QKD solutions, and we see that big money, especially money from government, big dollars are spent in that field. So I'm just addressing that if QKD vendors want this solution to succeed, they have to embrace open standard. They have to reject the vendor proprietary approach and vendor lock-in ideology and embrace open standard. This is like KMS in the past, right? In the past, all the KMS vendors implement their own proprietary protocols, and now we have KMIP, and everyone adopts KMIP and PKS11. That's the best. Yeah.
Hello.
Yeah.
You mentioned there are several different QKD schemes. Do you have any personal favorite which you believe will be the choice of the future?
First of all, I'm not an academic in that field. I'm not well researched. I cannot predict which technologies will become popular in the future. But what I'm saying, trying to convey the message is, there are technologies. QKD is not fully matured. There are many limitations, but there are technologies out there that can potentially address those limitations to make QKD system more useful in the future. Yeah.
Hey, Eric. Thank you very much for the presentation. And I would like to know, can you use like regular cryptography algorithms with quantum keys?
Sorry for your. I didn't hear.
So you have quantum keys. Can you use those keys to encrypt with regular algorithms, or do you need like some specific ones?
No. So based on my understanding, quantum keys are there's no there's no magic behind a quantum key shared in a QKD network. So it is all symmetric keys. So any applications can be benefited from these symmetric keys, can, in theory, utilize as a quantum key. Hope that answers your question.